Hello, my dear students. How are you all? I am Khandakar Fazl Rabbi, lecturer, Department of Chemistry, Milestone College, Uttara. During this pandemic situation, welcome you all to our chemistry online class. Today, I discuss about some important topics from chemistry first paper, chapter 2, qualitative chemistry, and now we discuss about the topic quantum number. Dear students, in an atom the electrons are accommodated in consecutive energy levels around the nucleus. These energy levels may be circular or elliptical. Moreover, the electrons do not just move around the nucleus but also spin around in their own axis, in its own axis. In order to represent these energy levels, size, shape of the energy levels, orientation of the orbitals, and the direction of the spin, there are some numbers which have been put into use. These numbers are called quantum numbers. That means the numbers which express the size, shape, orientation in the space of the orbital in the nucleus and the direction of the spin of the electrons in their own axis are called quantum numbers. So, according to our discussion, we can also say that quantum numbers are the numbers by which we get complete information about the electrons in an atom. We know that there are four types of quantum numbers. First one, principal quantum number. Second, azimuthal quantum number or subsidiary quantum number or secondary quantum number. Third one is magnetic quantum number, and the last one, that means fourth one, is spin quantum number. Dear students, now principal quantum number. The quantum number that expresses the main energy level in which the electrons are moving around the nucleus is the principal quantum number. Principal quantum number is denoted by n, where n equal to 1, 2, 3, 4 dot dot, where, and that is whole number. Okay, when n equals to 1, then it represents the first energy level, first energy level, that means K shell. When n equal to 2, it represents the second energy level, that means L shell. When n equal to 3, it represents the third energy level, that means M shell. And when n equal to 4, it represents the fourth energy level, that means N shell. So, According to Bohr concept, we get that the energy levels are like this: 1, 2, 3, 4. Okay, and this one for K, L, M, N, and for this case n equal to 1, n equal to 2, n equal to 3, n equal to 4. That means when n equal to 1, then we get K shell. When n equal to 2, we get L shell. When n equal to 3, then we get M shell, and when n equal to 4, then we get N shell. My dear students, now secondary or subsidiary or azimuthal quantum number. We know each principal shell is divided into several subshell. The quantum number which is used to indicate subshell is known as subsidiary quantum number or azimuthal quantum number or secondary quantum number. It is denoted by L. It may have the value from 0 to n minus 1. The values of L determines the shape of the subshell. That means when L equal to 0, then we get subshell S. When L equal to 1, then we get subshell P. When L equal to 2, then we get subshell D, and when L equal to 3, then we get subshell F. Dear students, here given the value of L and name of subshell. When the value of L equal to 0, the name of subshell is S, and source of name from spectroscopic line is sharp. Now, when value of L equal to 1, name of subshell is P, and source of name from spectroscopic line is principal. When value L equal to 2, the name of subshell is D, and source of name from spectroscopic line is diffuse. And when value of L equal to 3, name of subshell is F, and source of name from spectroscopic line is fundamental. Now, here we see that when n equal to 1, that means the value of principal quantum number equal to 1, then L equal to 1 minus 1, that means 0. So, we get only S subshell in first shell. Now, when n equal to 2, then the value of L equal to 2 minus 2, 2 minus 1, that means 0, 1. And for the value of 0 of L, then we get S orbital, and for L equal to 1, we get P orbital. Here we have to write the principal quantum number to S 2P. When n equal to 3, then L equal to 3 minus 3, 3 minus 2, 3 minus 1, that means 0, 1, 2. And for 0, we get 3S. For 1, we get 3P. And for 2 we get 3d orbital. And when the principal quantum number, when n equal to 4, then L equal to 4 minus 4, 4 minus 3, 4 minus 2, 4 minus 1. That means 0, 1, 2 and 3, and then we get 4s, 4p, 4d, 4f orbital. So we can say that first shell has one type of orbital, and second shell, that means when n equal to 2, then we get two types of subshell, that is 2s and 2p. When n equal to 3, that means third shell, we get 3 subshell, that means 3s, 3p, 3d. And when n equal to 4, that means for fourth shell we get 4 subshell, that is 4s, 4p, 4d and 4f. Magnetic quantum number. In center of an atom there is a positively charged nucleus and there are negative charged electrons revolving around the orbit. As a result, magnetic field is created. Due to the effect of magnetic field, different three-dimensional arrangement may occur. To express this arrangement, a new quantum number is introduced, which is called magnetic quantum number. Magnetic quantum number is denoted by M. Magnetic quantum number, magnetic quantum number is denoted by M. The value of M depends on the value of L, and it may have the value from 0 to plus minus L. That means magnetic quantum number is denoted by M. The value of M depends on the value of L. It may have the value from 0 to plus minus L, that means minus L to plus L, including 0. So according to our discussion, we can say that when L equal to 0, then M equal to 0. That means in S subshell, exists one orbital. That means when L equal to 0, then M equal to 0, and in S subshell exits one orbital. When L equal to 1, then M equal to 0 plus minus 1. That means minus 1, 0 plus 1. And in P subshell, exits 3 orbitals. When L equal to 2, then M equal to 0 plus minus 1 plus minus 2. That means minus 2, minus 1, 0 plus 1 plus 2. So, we get in D subshell exits 5 orbitals. And when L equal to 3, then M equal to 0 plus minus 1 plus minus 2 plus minus 3. That means in F subshell, exits 7 orbitals. So, the orientation of S orbital equal to 1, the orientation of P orbital equal to 3, the orientation of D orbital equal to 5, and the orientation of F orbital equal to 7. In quantum number, while electron rotating around the nucleus, the electrons also rotate around its own axis either in clockwise or anti-clockwise direction. Spin quantum number is used to describe this. Spin quantum number is denoted by S, capital S. For clockwise spin, the value of S equal to plus half, and we can also use upward arrow to indicate the clockwise spin. And for anti-clockwise spin, the value of S equal to minus half, and we can also use downward arrow to indicate the anti-clockwise spin. Dear students, now our question is why 2D orbital is not possible. Okay, for 2D orbital, the value of n equal to 2. Now, when n equal to 2, then L equal to 2 minus 2, 2 minus 1, that means 0 and 1. Again, if L equal to 0, then we get only S orbital. If L equal to 1, then we get only p orbital. That means when the value of n equal to 2, then we get only the value of L equal to 0 and 1. 0 for s orbital, 1 for p orbital. So when n equal to 2, then 2d orbital is not possible. Here n equal to 2, so only 2s and 2p orbital is possible, and that's why 2d orbital is not possible. Dear students, our next question is calculation of total orbitals and electron numbers present in different shells of an atom by calculating the value of n, L, m. Okay. Here given principal quantum number n, subsidiary quantum number L, subshell magnetic quantum number, and number of orbitals, number of electrons, and total electrons. Okay. Students, when n equal to 1, that means first shell, then we get the value of L equal to only 0. So the subshell is 1s, and for L equal to 0, we get magnetic quantum number equal to 0, and when m equal to 0, then we get only 1 orbital, and for 1 orbital we get 2 electrons. So total number of electron present in first shell equal to 2. Now when n equal to 2, then the value of L equal to 0 and 1. For 0 we get 2s subshell, and for 1 we get 2p, and when L equal to 0, then we get the value of m equal to 0, and when L equal to 1, the value of m equal to -1, 0, plus 1. So number of orbitals present for 0, here we get 1 orbital, and here the orientation of orbital equal to 1, 2, 3, so we get 3 orbital here. So the total number of orbitals present in second shell equal to 4, and for this orbital we get 2 electron, and for the value of 3 we get 6 electron, and total number of electron present in second shell is 8. Now when the principal quantum number n equal to 3, then the value of L equal to 0, 1, 2. So subshell is 3s, 3p, and 3d, and for this case the value of m, L equal to 0, so m equal to 0. When L equal to 1, m equal to -1, 0, plus 1, and when L equal to 2, then -2, -1, 0, plus 1, plus 2. So here we get 1, 3, and for 3d orbital we get 5 orientation. So the number of orbital present in third shell equal to 9, total 9. Okay, and for number of electrons, here we get 1, so it will be 2, 6 and 10, and total electron present in third shell, that is 18. And for principal quantum number n equal to 4, that means for fourth shell we get the value of L equal to 0, 1, 2 and 3, and we get subshell 4s, 4p, 4d and 4f. So the value of m equal to 0, -1, 0, +1 for L equal to 1, and when L equal to 2, then we get the value -2, -1, 0, +1, +2, and when L equal to 3, then we get -3, -2, -1, 0, +1, +2, +3, and we get the number of orbitals here 1, 3, 5 and 7. So the total number of orbitals present in fourth shell, that is 7, 5, 7 plus 5 plus 3 plus 1, that means 16 orbitals present in fourth shell, and number of electron 2, 6, 10, 14, that is total 32 electrons present in fourth shell.